we're going to go over heating and cooling curve calculations. So the first thing that I'm going to do is just draw a quick heating and cooling curve. We'll have either time or energy on the x-axis, on the y, temperature in degrees Celsius. Heating curve, we're going to start at a low temperature and the substance is going to heat up as we go. Cooling curve, just the opposite. We're going to start at a high temperature and it's going to cool off. Quick review from yesterday. At the lowest temperature represents when the substance is a solid. In the heating curve, the lower temperature phase change represents the substance melting. Cooling curve, that would represent when the substance is freezing. The solid melts into a liquid, so the middle diagonal on each curve represents when the substance is liquid. The liquid boils or evaporates into a gas. On our cooling curve, the gas condenses into a liquid. We are going to use different equations for each of the 5 segments. So I am just going to number each of the segments. Solid is going to be segment 1. Melting and freezing, the phase change between liquids and solids, would be segment 2. When the substance is a liquid, that will be segment 3. Boiling, condensing, the phase change between liquid and gas, segment 4. And when the substance is a gas, we're going to call that segment 5. So we are going to use a slightly different equation for each of these 5 segments. One thing that is really nice about this is the equations are going to look very similar, so it shouldn't be too hard to remember when we use which equation. So first, if there is a temperature change, you're going to use the equation Q is equal to mc delta T. So we have temperature changes, segment 1, segment 3, and segment 5. In this equation, Q is going to represent heat or energy. So if the question says how much heat is needed or how much energy is needed, both of those questions are asking about Q. M is going to represent the mass. Delta T is our change in temperature. The way we're going to calculate the change in temperature is by doing the final temperature minus the initial temperature. C represents specific heat. Specific heat is the amount of energy required to raise 1 gram of a substance by 1 degree Celsius. Every substance has its own unique specific heat, and it is also dependent on its state of matter. So if it is a solid, it's going to have a different specific heat value than when it is a liquid and when it is a gas. If we look at segments 2 and 4, we do not have a temperature change. Those are plateaus, they're flat, no temperature change during our phase changes. So we're not going to use Q is equal to delta T because we don't have a delta T. There isn't a change in temperature. So instead, what we're going to use, Q is equal to mass times the heat of fusion, or Q is equal to the mass times the heat of vaporization. The way I remember which one is which, vaporization, it sounds like evaporating. So segment 4, where it is boiling or evaporating, we would use the heat of vaporization. When you have a heating or cooling curve calculation, you're going to be given a whole bunch of information. So things that you'll have to be given. Heat of fusion. For this substance, our heat of fusion, 100 joules per gram. This tells us how much energy is required for our substance to melt. We're using it for melting and also for freezing. So how much joules of energy is needed for every gram of our substance? Heat of vaporization. How much energy does it take per gram to evaporate a substance? 1,000 joules per gram. You also need to be given your 3 specific heat values. For this substance, specific heat of the solid, 2.0 joules per gram degree Celsius. Specific heat of the liquid, 5.0 joules per gram degree Celsius. And C gas, 1.0 joules per gram degree Celsius. You also need to be either given a heating or cooling curve, or you need the phase changes to where you could draw a heating or cooling curve. For this substance, it is going to melt at a temperature of 15 degrees Celsius, and it is going to boil or evaporate at a temperature of 35 degrees Celsius. So we're going to do a few questions using this information. Number 1, calculate the energy needed to heat 2.0 grams of the substance from 5 degrees Celsius to 13 degrees Celsius. So we are going to calculate energy. Energy is Q. My mass, 2 grams. The initial temperature is 5 degrees Celsius, and we are going to heat it to a final temperature of 13 degrees Celsius. So the first thing that we should do after we define our variables is figure out which equation we're going to use. If you have a temperature change, you're going to use the equation Q is equal to MC delta T. Next, we have 3 specific heat values, C solid, C liquid, C gas. We need to figure out which of those we're going to use. And the best way to do that is to go to your heating curve or cooling curve and find the temperature range that you are given. We want to heat the substance from about 5 degrees Celsius to 13 degrees Celsius. Based on where we are in the curve, between 5 and 13 degrees Celsius, the substance is a solid. So that means I need to use the specific heat value of my solid. Once you figure out the equation, all you have to do is plug in your variables and solve. So my mass is 2 grams. specific heat of the solid, 2 joules per gram degree Celsius. And then we are going to multiply that by the change in temperature, final minus initial, 13 degrees Celsius minus 5 degrees Celsius, delta T, 8 degrees. 2 times 2 is 4. 4 times 8 gives me 32. Joules cancel out, degrees Celsius cancel out. We'll be left with joules. If we are rounding this to significant figures, final answer 30 joules of energy. Let's try another one. Number 2. Calculate the energy needed to heat 12 grams of liquid at 35 degrees Celsius to a gas at 35 degrees Celsius. All right, so now we don't have a temperature change. We're still solving for energy, so I want to solve for Q. My mass is 12 grams, but we don't have a change in temperature. We're starting at 35 degrees and we're ending at 35 degrees. If there's not a change in temperature, we're not going to use Q equals mc delta T. So we have to use Q is equal to mass times either the heat of fusion or the heat of vaporization. The way that we figure that out is by finding these two temperatures on our heating curve and picking the appropriate variable based on where we're at. So going back to our heating curve, I'm going from a liquid at 35 degrees to a gas at 35 degrees. This is where the substance is evaporating. Since this is evaporation, we're going to use the heat of vaporization. Heat of vaporization is given to us. The heat of vaporization is 1,000 joules per gram. Once you know your equation, all you have to do is plug in your numbers and solve. My mass is 12 grams. Heat of vaporization, 1,000 joules per gram. 12,000 joules of energy. Grams divided by grams cancel. We're left with joules. Let's try one more. Last question. Calculate the energy needed to heat 15 grams of the substance from 17 degrees Celsius to 32 degrees Celsius. So the first thing that I'm going to do is just go through and see what I know, see what I'm trying to solve for. Again, we're calculating for energy. Energy is Q. My mass is 15 grams. We are heating this from an initial temperature of 17 degrees Celsius, and we're heating it up to a final temperature of 32 degrees Celsius. We have a temperature change. Anytime we have a temperature change, we have to use Q is equal to mc delta T. Next, we're going to go back to our heating curve and we're going to pick out which specific heat value we need to use. And the way we're going to do that is by going to our heating curve and we're going to find these two temperatures, 17 and 32. So 17 degrees is probably right about here, 32 degrees right about here. At this segment, the substance is a liquid. Since it is a liquid, we have to use the specific heat value of the liquid, 5 joules per gram degree Celsius. From here, all you have to do is plug in your numbers and solve. Mass is 15 grams. Specific heat of the liquid was 5.0 joules per gram degree Celsius. And then lastly, we need to plug in our change in temperature by doing final minus initial. 32 degrees Celsius minus 17 degrees Celsius gives me a change in temperature of 15 degrees. If we were rounding to two significant figures, final answer 1100 joules of energy.